Well, let's continue, pardon me, chatting about finding inverses. We just started talking about inverses briefly at the beginning of the class last time. So remember that from a definitional standpoint, an inverse of a square matrix, so I'll say n by n matrix A, is a matrix B. Oops. So that if I take A times B, I get the same thing as if I take B times A, and I get the identity matrix. Since I went ahead and defined that A is an n by n matrix, when I multiply those two things together, I better also have B be an n by n matrix, because otherwise my multiplication is not going to be defined on both sides. And then I know I should end up with the n by n identity matrix. So again, remember we talked about the identity matrix last time. The identity matrix is what's basically behaving like multiplication by 1 for matrices. So an inverse gets you back to 1, gets you back to that multiplicative identity, just like it does for numbers, right? If we multiply by 3, undoing that multiplication is multiplying by a third, right? Same idea with matrices. If we multiply by a matrix A, I want to be able to undo that no matter which side I'm on. All right. Again, when we say we can do this on both sides, we refer to this as a two-sided inverse. So all of our inverses will be two-sided for matrices. It's possible that you have one-sided inverses in other algebraic structures. We won't be talking about those in here. All right. In any event, let's talk a little bit about how we do this. And we started talking about this at the end of class last time. Go back through it again, make sure that we understand what we need to do to find an inverse. So again, I'm looking for a matrix A, and I'll start it off with columns. So I wrote this down last time. So it's the same thing I wrote down last time. If I think about multiplication, I can write today, multiplication on the right by on the right side of A by some n by n matrix, I can think about looking at it as a column at a time. Again, we know that both my A and my inverse matrix has to be an n by n matrix. So I know I'm going to have n columns, and then each of these would have n entries in them. Or if you think about them as vectors, they would have n components to them. So again, when you do the multiplication, to figure out that first column of the answer, you take row 1 of A and match it with column 1. That gives you the 1, 1 entry. If you take row 2 of A and match it with column 1, that gives you the 2, 1 entry. And so on down the line, right? So we can think of that first column of the product as being just A, C1 as a column, right? I can take the whole matrix A, multiply that by the first column, that fills out the first column of the product. Because again, I'm just taking every row of A, matching with the first column. That's exactly how we fill out the first column, right? Do the same thing for the second column, and then all the way across to the last column. So this is just one way that we can think about multiplication on the left. I can think about the matrix just being multiplied on the left by each of the columns and fill out the columns. Okay. The reason that I want to think about it this way is because, again, I want this to be an inverse, right? So I want this to be the identity matrix. Well, let's think about what the identity matrix looks like. Well, the first column has a 1 in the upper left-hand corner, right? And then zeros all the way down. The next column is a 0 here, 1, 0, zeros all the way down, right? Third column, similar, until we get to the last column, and there's a 1 at the bottom. That's what our identity matrix looks like, right? It's that diagonal matrix that has 1s down the diagonal and 0s everywhere else. If this is going to undo multiplication by A, then that's what my answer should look like. Now I have two matrices, pardon me. Now I have two matrices that are supposed to be equal to each other. So this first column, this AC1 column, has to equal the 1, 0, 0 all the way down, right? The AC2 has to equal the 0, 1, 0 all the way down, and so on down the line. So we need to solve a whole bunch of systems of equations, basically, right? We want AC1 to be 1, 0, 0, 0. That should be C1. We want AC2. If I could stop writing the C's as subscripts, that would be fantastic. 0, 1, 0 all the way down. And all the way across till I get to the ACN being 0, 0, 0, 1. Remember, again, we're trying to undo that multiplication. We're trying to figure out what the first column has to be. So when we do the product, I get 1, 0, 0, 0, 0 all the way down. I want to figure out the C2 so that when I do the product, I get 0, 1, 0 all the way down. And so on down the line. That makes sense? Okay. Notice that these look like matrix equations, right? I can think about this as being a constant vector. I can think about this being a constant vector. I can think about this being a constant vector. This looks like a matrix equation representing a system of linear equations, right? Notice that your coefficient matrix doesn't change, right? It's the same coefficient matrix all the way around, all the way across. Now, with our first technique of solving systems of equations, what did we do? We put it in an augmented matrix and row reduce, right? So I would do the same thing here, right? I would take A, augment this, row reduce, see what I get to solve that one for C1. We agree? I would take A, augment this, row reduce, and get C2 all the way across. But if I'm row reducing, what matrix are you really row reducing? Does the constant matter, or is it the A that is the part that you're really worried about row reducing? The A, right? So the same sequence of row operations that row reduces A in the first system is the exact same sequence of row operations that will row reduce A in the second one, the third one, the fourth one, all the way down, right? So to solve this, we can just solve it all at once. We can take our matrix A and augment the identity matrix to it, and then put it in reduced row echelon form. What do we hope to see on the left-hand side if we're going to put an n by n matrix in reduced row echelon form? What do we hope to see if we're going to be able to solve this? If it's n by n, and we're going to solve it, when we put it in reduced row echelon form, what do we hope to see? What kind of matrix, what matrix should we see at the end? The identity matrix, right? I hope to see a 1 in that upper left-hand corner, and then another one that stair steps just down, and then another one, right? I hope to see the identity matrix here. And what we'll end up with is what we refer to as the inverse of a matrix. I know I defined it as an inverse, but we define that what should be here is the inverse, which will denote with a to the negative 1. Be careful, that's not an exponent. It's a notation for the inverse. It does not mean 1 over a. We don't do matrix division. We multiply by inverses. Okay? So don't ever put a matrix in a denominator. It makes absolutely no sense. Okay? Mathematically and notationally, it makes absolutely no sense. Okay? So don't do that. All right, so I've introduced a new notation. Notice that again, we said that the whole reason why we know this is going to be unique in this sense, and then we'll prove it here in a second. Yes. That's what our notation for the inverse matrix. I'm going to go over it some more here in a second, but that's our notation for the inverse matrix. Okay. because it turns out that inverses are unique. So we use that specific notation. But again, this is not an exponent, it's just our notation for the inverse, so we don't write it as a fraction. We write A inverse when we want to do the inverse matrix. Yep, you're welcome. All right, so again, the reason why we know this is unique in this sense is because, again, we said the same sequence of row operations that solves this system is the exact same sequence of row operations that solves this one, and so on down the line. So there can't be two answers. There's an answer, right? There's one answer. So we can't get a bunch of different ones. All right. Now, again, do we know that we will necessarily get the inverse, the identity matrix when we row reduce, or is it possible we might get a row of zeros at the bottom from what we've done before? Do we always get the identity matrix when we row reduce? No. So if we don't get the identity matrix when we row reduce, at least one of these systems will be inconsistent, and so it doesn't have an inverse. So that's how you can tell that a matrix doesn't have an inverse, is you'll end up, when you row reduce, you'll end up with a row of zeros somewhere at the bottom, and then that's telling you it's equal to something that's not zero, and so you get an inconsistent system at that point. Okay. So that's how we'll tell if we don't have an inverse. All right. So we'll do an example here in a second, but I really do want to do the proof where inverses are unique. So the theorem is if B and C are both inverses of a matrix A, then B has to be C. The reason why I want to do this particular proof is because this is a very, very common thing in mathematics. If you want to show something is unique, you assume you have two and show they have to be equal. Okay? This is a very, very common way to prove things in math for uniqueness. Assume you have two and show that they're the same. All right? So that's what I'm saying here. I'm assuming I have two inverses. I'm going to show that they are the same. This proof is very short. All right, so we'll suppose that B and C are inverses of A. Again, what does it mean to be an inverse of a matrix? What's the whole point of being an inverse of a matrix? What does that mean?
Or you guess multiply with the original matrix to form the identity matrix.
Good, that's exactly right. So we know that A times B is the identity matrix and the other way around too, right? It works on both sides because, again, by definition, matrix inverses are two-sided. So on the left and the right. The reason why we state this is because, remember, in general, matrix multiplication is not commutative, right? It doesn't necessarily work in either order. All right. So we know that A times B and B times A gives us the identity, and A times C equals C times A gives us the identity. I want to write this on the board rather than on the screen because I don't want you to write this down, but I do want to make a point of this. You might be tempted to say this is true, which it is in this case, that A times B equals A times C, since they're both equal to the identity matrix. Right? And remember, we're trying to get to B equals C, so what are you tempted to do at this stage? Yeah, divide out an A, right? You're tempted to do that because that's what you've been trained to do your whole life, right? I see it on both sides. Of course, if I say, even if you think about it as real numbers, if you divide out the A, what are you assuming that A is not equal to? 0, right? In matrix sense, if I want to multiply both, if I want to get rid of the A's, that means I need to multiply by A inverse. That assumes the inverse exists. So it's very, very tempting to say this by some cancellation property, right? I'm trying to cancel the A's off. But in order to do this, this assumes that A inverse already exists, okay? that assumes that we have some sort of a cancellation property that allows us to do this. So it's just like if you do this when you have like little a, b equals little ac, implies b equals c. This assumes that a is not equal to 0, which you don't necessarily know to start with. Okay. So as tempting as this is, don't do it. Okay. The only way that you can do it is if you know that the inverse exists to start with. So we'll prove this a different way. Okay. So just in general, know that you cannot necessarily cancel matrices on either side. Another thing that's equally as tempting and really doesn't work is if you have the A like this. The issue here is that my A is not on the same side. And do I know that I can flip this around? No. I don't know things commute. So this, I could never make this assumption. Unless your matrices happen to commute, then it'll work. But I can never cancel in that situation. Okay. And it's different than when you work with numbers, right? Because numbers, your multiplication works in both orders, right? In matrices, it doesn't. All right, so here's how we're going to start it. Remember, we're trying to show that B equals C. So I'm going to start with a line of things. May not have left myself enough room. I'm going to start with a line where I have B is equal to something that I know B is equal to, and then simplify until I get to know where something with C is equal to. Okay, so I'm going to make a line of equalities. All right. What can I multiply B by and not change anything? What matrix can you multiply B by and not change the B at all? What was it? I. Yeah, I can multiply by the identity matrix, right? So I can write B as B times I. That's weird. And write B as B times I didn't change anything, right? That's just how we formed the identity matrix. Do you see something that we've written down that I can replace I with that involves C? AC, right? Have that written down right here, don't we? Okay. So I can take out, why are you doing that? I can take out the I and put in an AC. I do need to move this over a little bit. Hold on, I didn't think I left myself enough room. Take out the I, put in an AC. Now notice that I put the parentheses around the AC because I'm taking out the I and putting AC in specifically for the I. What do I want to do with those parentheses? Yeah, move them over to the BA, right? Can we do that? And take the parentheses off the AC and put it on the BA? Yeah, we proved that last time, didn't we? Matrix multiplication is associative. I don't stop hitting things. That's just associativity of multiplication. And now do we know something that BA is equal to? I. So now I get I times C, and I times C is C. So this proves that if we have two inverses of the same matrix, then they really do have to be equal to each other. So that's why we use the notation of a to the negative 1, not really an exponent, but that's why we use that a to the negative 1 notation for the inverse. Okay. So since, I'll just write this down, since inverses now are unique, we write a inverse to denote the inverse of A, when, of course, the inverse exists. All right, so the only reason why I want to make sure, well, there's two reasons why I want to go through this proof. The first one was, again, this is a prototypical example of how you handle proving two things are equal, or excuse me, something is unique in mathematics. Assume you have to show that they are equal to each other. The other is that this allows us to introduce this notation now. This is why we use that a to the -1 notation for the inverse. Okay. All right. For some terminology, if I say a matrix is non-singular, this means that A inverse exists. So A is non-singular means the same thing as A is invertible, means A exists. If I use the word singular, that means that A inverse does not exist. So singular means does not exist. Non-singular means it exists. So far, so good? Ready for an example with actual numbers in it? Okay. All right. So we talked about how we actually do this. So let's do an example here. This is number 14 in your book. It's on page 71. 1, 2, 2, 3, 7, 9, -1, -4, -7 is the matrix. I'll call it A just to give it a name. We're going to find the inverse. Okay. So what we mentioned before is I'm going to take the matrix and augment the identity matrix. Really what we're doing here is we're solving three systems of linear equations all at the same time. That's all we're doing by augmenting an entire matrix on here rather than a single column. Okay. Again, if the inverse is going to exist, what do we want to see on the left-hand side? The identity matrix when we're done, right? If we see a row of zeros at some point, inverse doesn't exist. Matrix is singular. Okay? All right. Again, go through your normal row operation procedures. What do we want in the upper left-hand corner first? A 1. We got it, right? So we want to get rid of the ones below it, or the numbers below it. So we'll do -3, row 1, added to row 2, replace row 2. And we'll do row 1 plus row 3, replace row 3, right? I got to get rid of the 3, so I do the -3. I get rid of the -1, so I just multiply by a 1. Again, that doesn't change the first row at all, right? Doesn't change our first row at all. What's the second row become? It's a positive one, isn't it? Yeah, okay. Good. And you got to go all the way across. Be -3, 1, 0, right? Because I got to do -3 times the 1 and add down. What about the next column? Why did that do that? Go away. There we go. What about the last row? Good. Yep. Excellent. Oh, it's -2, isn't it? Because we had 2 plus the -4, so it should have been a -2. Easy to make those negative. I got to watch all those sign things, right? All right. What's the next step in the row reduction? So technically the next one is get a 1 right here, right? Which we have. So then we want to get zeros above and below it. What do we do? Yeah, negative 2 row 2 plus row 1 replace row 1, right? And then the other one's going to be good. Yeah, 2 row 2 plus row 3 replace row 3. Does that change row 2 at all? No. 0, 1, 3, negative 3, 1, 0. First row is what? So when are we doing this one now? 6 plus 1 gives me 7. Yeah. Negative 2 and 0. Going down now. They've rigged this one pretty nicely. Go on. They made this one nice without a bunch of fractions. It's easy to get a bunch of fractions in these. Okay. Are we okay with the first 2 steps? Next step would be to get a. We get technically to get a 1 where there is a 1, right? And the last step we'll get zeros above it. Okay. What do we need to do to get zeros above it? Okay. Oops, that's 2, yeah. Okay. Doesn't change the last row. The right-hand side is where all the magic's going to happen, so to speak. Because what's going to be left on the left-hand side when we do this row operation? Yeah, should be I at this point, right? Should be 1 0 0 0 1 0 at that point. That was what we were doing, right? Okay, negative 3 times negative 5 gives me 15 plus 7 is 22. Negative 6 plus negative 2 is negative 8. And then I get a negative 3 here. Or I'm doing the wrong thing, aren't I? Oh, geez. Try that again. See? Told you it's easy to make a mistake. I just did. Happens. Try that again. I'm doing the 4. Negative 20 plus 7 is negative 13. 8 minus 2 is 6. And then I get a 4. Now let's multiply by negative 3. 15 minus 3 is 12. Negative 6 plus 1 is negative 5. Negative 3 plus 0 is negative 3. What's left on this side is your inverse matrix. So we get negative 13, 6, 4, 12, negative 5, negative 3, negative 5, 2, 1. When we're done. Process okay? It's the same thing we've been doing, right? Not any different than anything that we've done as far as row reduction goes. Okay. One nice thing about these is you can check your answer, because if I multiply that by A, I should get the identity, right? I should get back to the identity. So you can check your answer pretty easily, right? Just multiply the 2 matrices together, make sure you get it. Of course, technology will do this for you too. So let me show you a couple of different things with technology, one on the calculator and one in R real quick. I know we haven't used R a lot, but again, I just want to kind of introduce things as we go along so we can see things. Let me get the calculator out first. I should have loaded this up before class, but I forget to do things sometimes. So that's part of my charm. What was that? All right, let's see here. All right, so let's just start with a matrix 3 by 3. The original matrix was 1, 2, 2, 3, 7, 9, -1, -4, and oops. Oh, goodness. I gotta get back on here. Delete. It likes the keyboard for some things and doesn't like the keyboard for other things. One of those is delete. Okay, and -7. All right. I think I got that entered in there correctly. Quit. To do the inverse of a matrix, I just need to grab the matrix. We've done that several times before, right? Grab the name of the matrix. Calculator will use the -1 command just fine and spit out the answer, and hopefully that was the same thing we got. Looks like it's the same. So you can use your -1 button on your calculator, your raise to the -1 power up button on your calculator, I guess I should say, and that will do the inverse on your calculator. Yes.
Well, raising the matrix to negative other power is interesting.
It'll do it, yeah. Well, the definition is to raise a matrix to a -2 power, you find the inverse and then square it. So you just kind of use those laws of exponents to allow you to break it apart as a product. So actually, you can do it either way. It's one of the things we can prove. You can do the inverse and then square it, or square it and then do the inverse. And either way works. We'll prove that too. All right. That's how you do it in your calculator. Pretty straightforward. In R, there's a little bit of a quirk you have to do. So, unfortunately, row reduction and finding inverses aren't in R built. I shouldn't say built in. You have to load a package to be able to do it. So, the first time you load it, you have to type in the following command. It's install.packages. That's the command to install package. You only have to do this once. Once you install the packages, they're installed. But you do have to use the next command every time you reload R. The name of the package that we're going to use is Pragma. It's like Practical Mathematics Applications or something. There's something it stands for. There's a whole manual online. We're not going to do much with it, but we needed to do a couple of the matrix operations that we're going to do. Okay. All right. When you install that, that's interesting. What do you mean not found? Oh, I know why. I forgot. You got to put quotes around it. I forgot. You got to put quotes around it when you install it the first time. Literally, you only have to do that once. Okay. Once you do that in R one time, it's automatically installed. After that, you just call the library each time. And then you don't need the quotes around it when you call the library because, of course, it's different depending on which command you use. All right. So once you get it installed, like I said, it's always installed. The way you get to use the different things is you use the library command. This does not require quotes. It's just library Pragma. Now a couple of the built-in operations in here are putting a matrix in a reduced row echelon form and finding the inverse of a matrix. Okay, those two things are in there. So let me tell you how you don't find the inverse of a matrix to start with. First, let's put in our matrix. Remember, we did this the other day. We use that matrix command, and then we can type everything in as a list. The way I'm doing it this way, and then I have to tell it. I know it's not very much fun to type this in. I probably should have used the rbind command. It would have been a little bit faster. Remember, again, I have to put in the entries of the matrix in a list, tell it how many rows, and then tell it that I typed it in by row. We did that. I know it's been a little bit, but we did that the other day. Okay. All right. Again, to see that I actually typed this in correctly, there it is. Okay. Good news is, once you load Pragma, if you want to use the Pragma operations for matrices, it'll do reduced row echelon form. RREF is the command for reduced row echelon form for a matrix in R. Now, here's the tricky. I just told you on your calculator you can just use a -1 exponent. What did that do to the matrix? Did it take the inverse? No, it just reciprocated all the entries. Okay? -1 power doesn't work for inverse matrices in R. Okay? The command is INV of the matrix. And then we get what we want. So, a little bit different. We've already saw a couple of little quirky things with that. Remember with matrix multiplication, we had to put the percent signs around the multiplication symbol. So, again, if you want it, the inverse command, like I said, isn't built in when you first load R. You have to load the Practical library, and then you can do the inverse. Yes?
You also only have to load the library once.
You have to load the library every time that you reload R, from what I've seen. It won't find it again. If you can find a way that'll load it one time, that would be fantastic. You only have to install the packages once, but every time I've opened R, I've had to reload my library. And I've done it on multiple machines. So unless there's some way to do it that I don't know, which is certainly possible, because there's lots of things I don't know. All right. Anyway, I just wanted to show you how you can do these in R. Like I said, we're just kind of building up a toolbox so that when we get to the point where we really would rather use R than our calculator, we'll be more comfortable with the commands. Okay. That's my whole goal of doing this. All right. Is okay? All right. Are you comfortable with finding the inverse through row reduction? That's the same process, right? And again, it's the same idea if you get to an inconsistent system. If you see a row of zeros, then you just say it's not invertible, and you're done at that point. All right. So let's talk about some other properties here for matrix inverse. One Ben alluded to a minute ago. If I take an inverse and raise it to the nth power, that's the same thing as taking the power and then taking the inverse. Either way works. This assumes we have an invertible matrix to start with. Anytime you see a problem where they've written down A inverse, unless it explicitly says show that A inverse exists, if they write the notation, you assume the matrix inverse exists. Okay. All right. So in order for me to be able to do this, this says I can do the inverse of A and then raise it to the n power. Notice that there is something being said here, because this says do the matrix operation first and then I can find the inverse. Okay. Now, since these are equal, this allows us to use the notation A to the negative n. Like we would multiply exponents there. Let's show quickly how this proof would go. All right. Remember that we said that inverses of matrices are unique. Okay? This notation on the right-hand side says I'm doing the inverse of A to the n. Okay? So what we're going to do is we're going to show that this behaves like the inverse of A to the n. And so then it must be the inverse of A to the n. Okay? So let's multiply a to the n times a inverse to the n and see what we get. Okay. Now, can I automatically pull out an exponent? No, because that would imply that the matrices commute, right? Notice that a squared b squared means AABB, right? AB squared means what? AB, right? These are not necessarily the same for all matrices. Because notice I got a different order in there, right? Okay. So for matrices in general, I cannot pull out the exponent, right? However, one of my matrices is A, and one of my matrices is A inverse. What do you get when you multiply that together? If I take A and A inverse, what do I get? Identity. Does it matter which way I do it? No. So A and A inverse do commute. So I can pull out the nth power here. Okay? That's a special case. It's because they commute. Okay? You cannot do that in general. Okay. It's important. That is not a general property of matrices. This is a special case because the matrices commute. Okay? But now what is A times A inverse equal to? You just told me a second ago. I, and certainly if I raise I to the nth power, what do I end up with? I. Okay. All right. So notice that this, what we just showed here is that this matrix behaves like the right inverse of this matrix. I need to show it on the other side. Remember, matrices have to be inverses have to be two-sided. Okay. So I need to do it on the other side, but the other side looks exactly the same. Move it on the other side. Again, since they commute, I can pull out the exponent. And then A inverse times A is also I, and I to the n is I. All right. So this matrix, A inverse to the n, behaves like the inverse of A to the n. Well, if it behaves like the inverse, it must be the inverse because they're unique. Okay? So that's the end of the proof. Since inverses are unique, we have that A inverse to the n is the inverse of A to the n. Works the same way with transposes. If you take the transpose of A and then do its inverse, you get the same thing as taking the inverse first and then do the transpose. Okay. Again, this notation is saying I want the inverse of the matrix I'm calling A transpose. Okay? So what we want to do is show that this behaves like that inverse of A transpose. Okay? So the proof is going to look a lot like what we just did a minute ago. I'm going to take A transpose and multiply it by A inverse transpose. I want to show that this behaves like the inverse. So what do I want this answer to turn out to be when I'm done? The identity, right? If it's going to behave like the inverse, and I need to see identity when I'm done, right? Okay. Last time we talked about a property of transposes with respect to a product. If we have AB transpose, what was that equal to? Yeah, remember, you can distribute the transpose, but it has to it reverses the order, right? But of course, it works both ways. So if I had this, I would know it's equal to this. How can I use this property to help me rewrite what I have on the screen there? Okay, is it A inverse or A inverse A? Technically, using that property, it's A inverse A, right? It's reversed. Now we know that A inverse and A commute, but technically, the order is reversed, right? A inverse times A is equal to what? Identity. And if you transpose the identity matrix, it's diagonal. If you don't transpose the identity matrix, what do you end up with? The identity matrix, right? Everything off the diagonal is 0. So if I do that reflection, I just get zeros getting flip-flopped with zeros. I get the same thing back. That makes sense? Now again, technically we need to show it on both sides because inverses need to be two-sided. Showing it on the other side, again, I can do the same thing. When you pull the transpose out, what does the inside look like in this case? Yeah, A inverse, right? Because again, it flips it, right?
Wouldn't it the first one be A transpose to the inverse? Because that's the same equation as the first one, is it not?
What'd you say that again?
Like in the first equation, you did A transpose times A inverse transpose.
Yep.
But that's the same thing as the next equation.
This one.
Or is it just a different because it's flipped?
It's flipped, yeah. Because remember, when I'm trying to show something as an inverse, I have to show it on both sides. So I have to show both products work. That's why I flipped it around. Okay. You're right. It is. It looks exactly the same thing, but I flipped it. Yeah. And then AA inverse is equal to I again, and transpose the identity is the identity back again. Okay. So again, same idea. Since inverses are unique, the inverse of A transpose must be the transpose of A inverse. Last one, I got 2 minutes. I'm not going to go through the proof. I'll let you leave the proof for you. But I will mention what the property is here. This says do the product and then do the inverse. Let me ask you a question. Before you go leave your room in the morning, put socks on, put shoes on. Come back home in the evening, what comes off first? The shoes and then the socks, right? If you're trying to take your socks off first, you're going to rip your hole in your sock. Right? Okay. All right. So this is This is reversing the order, right? I'm sorry. This is inverting. This product is going to reverse the order when you're done. So the inverse of AB is B inverse A inverse. You'll prove it the same way. You'll want to show that AB times B inverse A inverse is I, and the other way around. Same idea. We're going to show it behaves like an inverse, so it has to be the inverse. If it walks like a duck and talks like a duck, it must be a duck. That's the idea. Okay. All right, so that's pretty much inverses. Next time we'll talk about elementary matrices in the next section. This web assigned due on Tuesday. What is it, section 2.3? Close around. We'll talk about 2.4 on Monday, and that'll be the last section that'll be on the exam. Right, so we'll do that on Monday. So remember again, exam either Thursday or Friday. Pick a day. Let me know what time you want to come in. Okay. Just send me an email about what time, what day you want to come in. Anyway, have a good weekend. See you on Monday.